Well done for completing the first 7 sections. You should now be familiar with some of the principles behind resistive and capacitive loads and their response to the electrical network. Today we'll be looking at inductors, which also have an interesting effect on the AC and DC systems. The aims of the course today are to show what happens when we connect inductors to AC and DC systems, to introduce the theories of inductive reactance, to show how the inductor affects the power factor, Inductors have the following details. The symbol is a coil of wire, because that's what an inductor is. The label is L. The units are henries or H. Let's now see what an inductor is made of. An inductor simply consists of a coil of wire wrapped around a metallic core, as shown here. As the coil is energized, it creates a magnetic field north and south. As the number of turns of wire on the coil increases and its magnetic effect increases, so does the value of the inductance. Let's now see how an inductor reacts when a DC supply is connected to it. Here we have an inductor connected to a DC source with a positive and negative connection. As the DC current starts to flow, it magnetizes the inductor, and the voltage across it grows. Once the inductor is fully magnetized, i.e. saturated, the flow of current will then stop. The inductor remains charged and the voltage potential remains across the inductor terminals. If the battery is then removed and replaced by a load, the inductor will discharge its stored energy into it. Let's now see how an inductor reacts to an AC supply. This is the same circuit as before, but this time we've got an AC source with a live and neutral instead of the DC source. As it's an AC source, we will be applying a sine wave that goes positive and negative. As the AC voltage goes through the positive cycle, it magnetizes the inductor. As the AC voltage goes negative, it demagnetizes the inductor. And this cycle continues time after time. This magnetizing and demagnetizing cycle by the inductor disrupts the AC power flow. The value of this disruption is called the inductive reactance. Let's now look at how an inductive load affects the current and voltage waveforms. Here's our standard amplitude time graph. Let's add the voltage sine wave as normal. Now let's add the current sine wave. The phase angle is the angular difference between the voltage and current waveforms. In a circuit containing a purely inductive load, the current lags the voltage waveform by 90 degrees. Let's look at that on a phasor diagram. First, let's show our voltage vector. Let's make a horizontal line as a reference point. Let's show our current vector. For a purely inductive load, the current lags the voltage waveform by 90 degrees. Therefore, phi is 90 degrees. The power factor is cos phi. Therefore, the power factor is 0. Let's look again at the power relationship. Power equals voltage times by current times by power factor. In inductive load, the power factor is 0. Therefore, the power is 0. How can this be? During one complete AC cycle, the inductor magnetizes and demagnetizes as the sine wave goes positive and negative. Therefore, no energy actually flows into the inductor. In practice, all loads consist of some resistive and some inductive elements, so the phase angle or power consumed is never actually 0. For the resistive inductive circuit, the impedance Z equals resistance R plus the inductive reactance XL. As XL is 90 degrees away from R, we give it a J or imaginary suffix. Therefore, Z equals R plus JXL. All three components are measured in ohms. Let's look at how to calculate XL, the inductive reactance. XL equals 2 times pi times F times L, where XL is the inductive reactance measured in ohms, pi is the constant 3.14, F is the frequency measured in hertz, and L is the inductance measured in henries. Let's do a worked example. For the 50 Hz system, what is the inductive reactance for a 3 Henry inductor? From the previous slide, XL is 2 times pi times F times L. Therefore, putting the numbers in, XL is 2 times 3.14 times by 50 Hz times by 3 Henries. Therefore, XL is 942 ohms. It can be seen that as the inductive value gets larger, its inductive reactance increases, and it has a greater impact on the AC system. Let's now look at the impedance relationships on a phasor diagram. First we have the resistance, measured in ohms. Let's make a horizontal vector as a reference point. Next we have the inductive reactance XL, also measured in ohms. It's 90 degrees away from the resistance vector. And finally we have the impedance Z, also measured in ohms. That's the summation of the resistance and inductive reactance vectors. The angle between the resistance and impedance vectors is the phase angle. By knowing any two of the above elements, Z, R, XL or phi, we can work out the value of the others using basic trigonometry. Just a final thought to finish. A good way to remember the current and voltage relationship with inductors and capacitors is an acronym. Firstly, C, I, V. In a capacitor C, the current I leads the voltage V, CIV. Then VIL. In an inductor L, the voltage V leads the current I, VIL. Let's put them together, we end up with civil. It's a nice easy way to remember the relationship. Let's now summarise what we've learned today. When we connect an inductor to a DC circuit, it becomes magnetized. After a while, it becomes saturated and the current stops. When we connect an inductor into an AC circuit, it introduces an inductive reactance which affects the power flow and power factor. In an inductive circuit, the current vector lags the voltage vector. Congratulations for making it through 8 sections. The end of the course is now in sight. I have attached some test questions in the course content. Please try them before going on to the next section, which will look at the power of an electrical network.